Hello everyone, here's a video on isotopes and counting protons, neutrons, and electrons within those isotopes. Okay, an isotope by definition, I don't think, there it is, it says atoms of the same element that have different numbers of neutrons. So an atom has to have certain consistency, and then now I'm just mentioning that there is things that are different. So if we take a look at perhaps, let's see here, hydrogen's listed below. Notice if it's hydrogen, it has to have a certain same number of protons, a certain same number of electrons, but it will have different numbers of neutrons if there are different isotopes. So again, how many isotopes do you see here? There are 1, 2, 3 versions of hydrogen, so there must be 3 isotopes, or atoms of the same element. Again, it must be hydrogen, because that's what we're calling it, and that have different numbers of neutrons. So let's take a look at how we represent this. And now, the atomic number is actually, they're both important. Atomic number, I think, might be a little bit more important than the mass number. But it's the number of neutrons in the nucleus. Excuse me, protons. Oh my gosh, I just made a huge mistake. It's the number of protons in the nucleus. And that's the identity of the atom. So if you have 6 protons and you look on a periodic table, man, that's carbon. If you have 11 protons, that has to be sodium. If you have 1 proton, that has to be hydrogen. You can't say, you know what, I want some sodium today, but I don't want 11 protons. I only have a 12 proton sodium. And you can have 12 proton sodium because that's going to now be magnesium. Okay, so just be careful on that topic. The identity of the atom is the number of protons it has, and that is called the atomic number. The mass number is the mass of the atom, in other words. It's the mass of the protons and neutrons. Well, where are the neutrons? They're in the nucleus. So the mass number is the number of protons and neutrons added together. Okay? Now, the way we do this is the mass number will typically be a whole number. Now you're going to say, well, when you look at the periodic table, it's all decimal, so I'll get to that in a second. Okay? So if we take a look at what I underlined here in red, this bottom number is the atomic number. There's the atomic number. Notice it's the same. Why? It has to be 1 because the atomic number of hydrogen is 1. How many protons does hydrogen have? The atomic number is the number of protons, so the answer to that question is 1. Okay, now the top number is the mass number, and the mass number is protons plus neutrons. So if I have this one right here, we must have 1 proton and 0 neutrons. For this one, we must have 1 proton and 1 neutron. 1 plus 1 is 2. For this one, we must have 1 proton and 2 neutrons. Notice the number keeps changing because these are 3 isotopes of hydrogen. How many protons? 1, 1, 1. How many neutrons? 0, 1, 2. How many electrons? Now that's a little bit of a different story here. If we have an atom, we assume that the pluses and minuses, the protons and electrons, are exactly the same. If I mention something called an ion, that's something different. We'll get to that later. But an atom assumes electrical neutrality, which means your positives, your protons, must be equal to the electrons, the negatives. Okay? So if we take a look at uranium down here, uranium, how many protons does uranium have? Let's look at this uranium here. It must have 92 protons. So protons, neutrons, electrons, it has 92 protons, and it must have 92 electrons because we're assuming it's the uranium atom, which again assumes positives and negatives are exactly the same. The question is, how many neutrons does it have? Well, if this number is protons plus neutrons, and this number is protons, then what should I do with those two numbers? You probably should subtract them. So 235 minus 92 is 143. So this has 143 neutrons. Okay? Going with this uranium over here, this is a different isotope of uranium. Again, protons, neutrons, electrons. How many protons does it have? It must have 92 because that's the atomic number. Same with the electrons. But now we have 3 more neutrons here than we had over here. So this must be 146. Okay, different, again, because it's 92 protons, it must be uranium. They both must be uranium, just that this one that I outlined in black is a little heavier. Okay, but they still act as uranium. Let's look at the hydrogen atom. I believe I have a graphic of that coming up here. Here's a good way to look at this. How many protons? 1, 1, 1. It's hydrogen. How many neutrons? 0, 1, 2. And how many electrons can we assume? 1 electron, 1 electron, 1 electron, because they will equal the positives. So how many protons, neutrons are in the following? So I have gold, 197. Okay, I've left off some numbers. This is actually called the, I forget what the notation's called. It doesn't really matter, but there's 2 ways to represent these. With this first one with gold, which is AU, gold is an atomic number of 79. So we'll plug that in there. So how many protons does gold have? 79. How many electrons does gold have? 79. How many neutrons does gold have? Let's get out my calculator. That's 197 minus 79 is 118 neutrons. I just subtracted the 2. Okay? Now, I'm sorry, by the way, this is called nuclear symbol notation. This is called hyphen notation. Okay? With hyphen notation, we now look at strontium. This is the mass number. This is A. Okay? This is the mass number. Okay? So the mass number is there. It's 90. So I don't know the atomic number, where the atomic number is represented by the letter Z. And if I look at strontium, it's 38. So how many protons? So I needed a periodic table to look that up. So protons are 38, electrons are 38, and neutrons, I'm going to subtract 90 minus 38. Oh, geez, what's 52 maybe? 90 minus 38 is 52. Okay? So that's calculating protons, neutrons, electrons. Here's more examples. See if you guys, again, if you ever need to pause it, you can work with this. So again, I have barium, that's Ba, and barium's atomic number is 56. So it has 56 protons, 56 electrons, and 138 minus 56 is 82 neutrons for this. And again, you can keep doing this. Phosphorus is another example. Okay? Now, here we go. Let's take a look at this. So if we have magnesium, it has 3 isotopes with the mass numbers of 24, 25, and 26. It says write the complete chemical symbol for each. So the chemical symbol notation is we're going to put magnesium. There's 3 isotopes, so let's write it 3 times. Okay, and then I'll put the atomic number of magnesium in green. And the atomic number for magnesium is 12, and that goes on the bottom. That's the number of protons. And since it's an atom, it's also the number of the electrons. Okay, and then the number of neutrons, I'll put the mass number goes on top, which is protons plus neutrons. So we have 24, 25, and 26. And it says how many neutrons are in each atom. Well, it looks like it's 12, 13, and 14. Okay, I just subtracted those numbers. That answers part B. Okay, moving one step further. Okay, so if I have these things, what you see on the periodic table is called the average atomic mass, okay? Now, everything I just showed you was a whole number, but when you look on the periodic table, they're all decimals. So if you look at chlorine, the average atomic mass of chlorine is 35.45, okay? So if chlorine on the periodic table, the mass number is 35.45, okay? Where does this number come from, and why do we have 0.45 if you can't have a fraction of a proton or a fraction of a neutron? It's because it represents the average of all the chlorines that exist. And the way that they solve this is this way. If there's 75%, 75.78% of chlorine has an atomic mass of 34.969, and 24%, 0.22 actually percent, is chlorine 37, which has a molar mass or atomic mass of 36.966. It says calculate the atomic weight. And what we're going to do is we're going to take the mass. Okay, so chlorine 35 has a mass of 34.969 AMUs, which stands for atomic mass unit, and we're going to multiply that by the percentage, but a decimal percent, so 0.7578, okay? And then we're going to take, so that we have a ton of chlorine 35. And there's lesser amount of chlorine 37, which now has a mass of 36.966, and we're going to multiply by its percentage, which is 0.2422, okay? So let's get some numbers here. So 34.969 times 0.7578 says that we have 26.5, let me move this, 26.5 of the chlorine 35, okay? That's the total percentage of chlorine of this mass right here, okay? Notice we're real close to 35, okay? 35.45. So let's take the other one, 36.966 times 0.2422, and you end up with 8.95, okay? Or let's say 8.9. Let's see how close we get. Well, since this and this add up to 100%, then this plus this must give us our total. So 8.95 plus 26.5, oh geez, oh Pete, I just screwed that up. Okay, 8.95 plus 26.5 give us a mass of 35.45. So that's how you solve this. So the answer here is this here. So I just did that by multiplying its atomic mass unit times the percentage that they exist in. Okay. I think there's one. Okay, I'm done for that. I'm done with that. So check that out, and if you have questions, go ahead and email.